prepared a couple of philosophical remarks about the state of confusion that we're in and so forth. And I was prepared to spend a few minutes venting, or whatever the word is called. But then one of my students reminded me that the last time I gave this talk, it took 2.5 hours at Stanford. So I decided to cut the philosophical remarks to just something very short. The very short thing is that I hope everybody realizes, in particular those people who are advocates of eternal inflation, what an enormous crisis this business has become. The issue of measures is a big one, in my opinion, and I don't think it's going to get resolved in an easy way. I think it's going to take a major collection of new ideas and a new paradigm shift that neither I nor N-1 of the people in this audience know what it is, and I'm kind of reluctant to even think that there's one who does know, but maybe there is one, but since nobody agrees, it's at best 1 out of N. So that was what I was going to talk about a little bit, why I see such a crisis, but I think it's so apparent with things like the Guth Van Turen, end of time, not the Guth Van Turen end of time, but the Guth Van Turen, the end of time. But even more than that, the inability to find any principle that would govern the choice of measure. And of course, we can't live without a measure. Without a measure, you can't have science. Everything becomes chaos. Anything can happen. And to me, it looks like this is one of these situations where a big crisis, a big conflict of principle are occurring, and that's scary. But it's also an incredible opportunity for new ideas. So, all right, let's put that to rest. What do we do when we face these kind of crises of principles? Different people do different things. Some make up wild and silly theories. Other people fall back on basic principles. Basic principles like the second law of thermodynamics, locality, the use of quantum mechanics when appropriate, and so forth. I belong to the latter camp. I'm a conservative, and so I feel strongly that we need to go back to some collection of trusted, really trusted principles. I outlined 3 of them. The second law, to me, is sort of sacred. I wouldn't play with that. Locality, well, we could probably fudge about that a bit. Black hole horizons and this and that, and string theory, they're a little bit non-local, and black hole horizons are somehow, in some sense, very non-local. So maybe we can fiddle with that a little bit. Quantum mechanics, I do believe deeply in quantum mechanics, but quantum mechanics when appropriate. It is not entirely clear to me that quantum mechanics is an appropriate tool for the multiverse as a whole. In fact, I rather doubt it, but quantum mechanics when appropriate, and of course in different people's eyes it will be appropriate in different situations. I don't think we're going to get away with the easy way of drawing Alan's big giant painting on the blackboard of a multiverse that extends up to infinity, which is painted by a classical painter, and then try to, I think Alan would agree, of course, that that is not going to be sufficient to resolve these puzzles of measures and so forth. So that kind of thinking I don't think is going to bring us where we want to go. I would add to the 3 principles, or the 3 refuges that I tend to take when I'm thinking about way over my head, I would add to those 3 things that we learned from black hole physics, which I think are extremely important and we cannot afford to neglect them. The first is entropy bounds. Bounds which tell us the amount of information which is realistic to have in a region of space. Very, very little of of the conversations that have taken place here have even mentioned that. I don't even remember if you mentioned it, Raphael. Did you? No, no. This is one of the basic things that we've learned about physics, that entropy is more bounded than we ever thought, and that means that information, in some sense, is much more restrictive or much smaller in amounts than we ever expected. Entropy bounds the holographic principle. Now, the holographic principle, of course, is connected with entropy bounds, but I want to say what I mean by the holographic principle. I most certainly do not mean what's called DSCFT. DSCFT, in my mind, has nothing to do with the holographic principle. The holographic principle discusses the number of degrees of freedom that it takes to describe a region of space, and the answer is 1 per Planck area. Whether or not DSCFT makes sense, there is no sense at all in which the future boundary, or let's say the regulated future boundary of de Sitter space, is described by a number of degrees of freedom which is 1 per Planck volume. That is an extraordinary overcounting of degrees of freedom, and so there's no sense in which, in my mind, DSCFT is the holographic principle in operation. You could call it a boundary theory, but it is not the holographic principle in the sense of counting bits of information. Information in the sense of quantum information. And the other thing which I think we should keep in mind, exactly how to use it is not clear, but we need to keep in mind, is the idea of complementarity of the two sides of a horizon. It's pretty clear that a lot of our grief or a lot of our confusion has to do with space-times with horizons, things out of causal contact with each other. The fact that nobody, perhaps that's not true, but perhaps I will say it now, nobody can know what's beyond their own horizon, and for that reason, the whole idea of a global multiverse having scientific meaning is a little bit comes into question. Technically, in black hole physics, we've discovered that information on the two sides of the horizon are not different information. They're redundant information about the same thing. How that can fail to be important in the context of cosmology, I don't know. And by ignoring it, I think we make very big mistakes. Okay, that was the rant. I made it longer than I thought I would, which means my talk is going to be shorter than I thought it was. There's another subject which is full of angst and confusion, and that's the foundations of quantum mechanics. The foundations of quantum mechanics are also very confusing. After a lot of thinking, Raphael and I, completely independently, began to think that maybe these two kinds of problems are connected with each other. That's not to say that one will solve the other. No way about it. No, that's not correct. But that they're connected, that the two kinds of confusions may reveal things about each other. The confusions about the foundations of quantum mechanics and the foundations of cosmology. So that's what I'm going to talk about. I'm going to talk about the paper that Raphael and I wrote, which is sticking our necks out a little bit. Both of us have tenure, so we didn't have to worry about it. So the paper we wrote about, from my point of view, from the way I think about it, which is a little bit different than the way Raphael thinks about it, but that's okay, close enough. There are three fundamental puzzles about quantum mechanics, and I'm going to organize the talk about these three different questions. The first question is, I'll state it. I was going to write it on the blackboard, but I write slowly. At what point do the virtual realities described by a wave function, at what point do the virtual realities become objective realities? This is the question of wave function collapse, if you like. We'll come back to it in a minute. And is there a point at which the virtual realities in quantum mechanics become real realities. Second, what is the meaning of probability? Now, I'm sure you're thinking in your head, oh boy, he's gone off the deep end. He used to be a good physicist, now he's talking about the meaning of probability. Perhaps. But I think we've seen in this conference that the meaning of probability is something that may be a little bit slippery. Third, who or what gets to observe the whole multiverse? In a quantum mechanical sense, observe. In the language of Alan, who or what is the multiversal archivist? Did I get that right, Alan? The multiversal archivist. Is there one, or is it just a fake that is meaningless? All right, those are three issues. Let me discuss for a minute three fictions that we ordinarily assume about, whether they're fictions or not remains to be seen, but we usually think of them as fictions. The first fiction has to do with wave function collapse. That has to do with the first issue. When do the realities become realities? When the wave function collapses. Now, there are many reasons to think that the wave function collapsing is a fiction, but one of the reasons is that wave function collapse need not be irreversible. So I would say the fiction, among other pieces to it, is that wave function collapse, whatever it is an irreversible phenomena, so that when virtual realities become real realities, is that reversible? Can things unhappen, is the way that we expressed it. The second issue has to do with probabilities, and the fiction that we adopt all the time, I guess we would call it the frequentist fiction, is that the probability for A is equal to the limit as n goes to infinity. This has been written on the blackboard any number of times at this conference. NA divided by n total. You know exactly what I mean, so I'm not going to explain it. The fiction, of course, is that we can let n go to infinity. That it means anything to let n go to infinity. We imagine that that's what probabilities mean. On the other hand, we know very well that not only can experiments two things. First of all, they haven't been done, and they won't be done an infinite number of times. And second of all, they can't be done an infinite number of times. So that's a second fiction. The third fiction, which is Alan's fiction, it's his private fiction, is that there is a multiversal archivist. The multiversal archivist records things. And of course, anybody who records things necessarily in quantum mechanics interferes with the system. We don't want anybody coming along and sticking their finger into the system and modifying it. So the multiversal archivist is at best a convenient fiction. I think you would agree with that, but I don't. Those are three fictions. And I'm going to deal with those three fictions, or three questions, with three postulates. We'll come to what those postulates are and discuss their relationship of these postulates to eternal inflation. Okay. Let's begin with the idea of decoherence. Decoherence is the modern version of wave function collapse. I think you all know it, and if you don't know it, learn it because it's important from papers like Zurex and other people, that wave function collapse was really a primitive way, or an older way, not a primitive way, an older way of speaking about what we now speak about when we say systems become entangled either with the environment or with the experimenter or with the apparatus. And I'll just give you an example, a quick example. The quick example is, of course, the two-slit experiment. Particles go through the two slits. I'm not even interested in whether in putting a screen here. Let's just say when they come out over here, they come out with a wave function, which is a superposition of a wave function going through the top and going through the bottom, psi 1 with a complex number, beta psi 2. And the complex phase between these is, of course, what accounts for the interference if you do shine it on a screen. But whether we shine it on a screen or not, we have a coherent superposition of two states, and in no sense can we say the particle passed through the upper trajectory or the lower trajectory. We just have to say, so far, nothing has happened which would tell us which of these two things happened. All right, now if we compare that with the situation where we put a detector over here, then what happens is that if the photon goes through the upper branch, it excites the detector, and the photon becomes entangled with the detector. The detector-photon system is still pure, but the detector has become entangled, and the result is if they only look at the photon or electron, or whatever the particle happens to be, the density matrix of it is reduced to a diagonal density matrix in some basis, and the off-diagonal things which are sensitive to the phase here, the phase between these, just disappear. That's a modern way of talking about wave function collapse. It happens when you put a detector there and you turn the virtual reality into a real reality. But of course, if you look at the bigger system, detector plus electron, it's still in a pure state. Well, the next thing that might happen is the detector. One thing I should say is that the entanglement between the detector and the system here is most certainly undoable. In other words, it's reversible. It may be hard to reverse if the detector is a big, complicated detector. It may be very, very difficult. But in principle, you can imagine a set of mirrors which would reflect the photons back and cause the detector to undetect, and in the process undo what happened. We call it unhappening. Happening can be followed by unhappening in principle. And so, at this stage, still, in a certain sense, nothing has happened objectively in the sense in which I will mean it. Okay, what happens next? Well, the detector might emit a photon. And the photon, the state of the photon might depend on whether the detector did or didn't detect. So now we have entanglement with the photon which goes off. And once that happens, we can now say something happened. The photon went through the upper branch, made the detector detect, and it didn't go through the lower branch. That becomes an objective fact. But of course, if we take into account the whole system, again, it is in a coherent state. We could put another mirror out here and undo it. So the question is there ever a sense, and what does it take to have irreversible decoherence? Now, irreversible doesn't just mean that you didn't reverse it. It means that you can't reverse it. Right? Is there any situation or any set of elements that would resolve this hierarchy of entanglements and tell us at this point something definite happened because nobody can reverse it? So let me state postulate 1 and tell you what we think the resolution of it is, or a resolution. It may not be the only resolution. Postulate 1 is simply that things happen. To say that things happen, I don't want to write it. Say that things happen means that there's a mechanism for irreversible decoherence. That's what it means. There exists a mechanism for irreversible decoherence. To keep it short, I'll just tell you how we think this plays into questions of cosmology. And so let me imagine then an inflating universe, a causal patch. Oh, let me tell you what this postulate rules out very quickly. It rules out closed cosmologies, cosmologies which are thermodynamically closed or dynamically closed. The reason is that dynamically closed cosmologies eventually will undergo recurrences. Recurrences, quantum recurrences. Now, don't worry about the time scale for it. We're trying to make some exact statements. The time scale is, of course, very, very long, but recurrences, among other things, restore coherence. So any system which is in a box, so to speak, in a sealed box, will violate this principle. I know two cosmologies which are in closed boxes. One of them is eternal de Sitter space, which is a closed box with finite entropy. Incidentally, it's the finite entropy which allows the recurrences. Closed, I don't personally think there is such a thing as completely stable de Sitter space. But if there were, I would put that in the category of closed box cosmologies. And if you wait long enough, what happened will eventually unhappen. Anti-de Sitter space is also another example. Anti-de Sitter space is an even better closed box. It's a better closed box as it really exists, mathematically. Yeah. No. No. Black holes return their information. They're just particles. They're just big particles with lots of states. Right? So, but you're on the right track. You're nevertheless on at least what we think is the right track. All right. So, ordinary de Sitter space, ordinary anti-de Sitter space, not good. What lets you out of this paradox or puzzle or in eternal inflation is the same thing which Alan addressed during his talk, the fact that de Sitter space can't last forever. In fact, it can't last anything like the quantum recurrence time, not even remotely. Just to remind you, the quantum recurrence time is a double exponential, not a single exponential of entropy. So long before any kind of recoherence can happen, recoherence of the whole thing, any kind of recurrence, de Sitter space will decay, of course. But let's forget that for a minute and just think about de Sitter space with a causal patch and a laboratory in it. And in the laboratory, experiments are going on. Those experiments may be like this experiment over here, and the experiments will emit photons, and those photons will go out. You can put mirrors there. The mirrors can reflect them back in. Decoherence can become recoherence, and you haven't yet achieved the situation where complete irreversible decoherence happens, but now I'm sure that Jim can tell me what the next step is. And the next step is to say there are event horizons. And once something passes out of the event horizon, it's gone. It cannot recohere. And so I would say that event horizons are an ingredient which potentially could bear on this issue of irreversible decoherence. It allows irreversible decoherence. So that was question number one. When do things happen? When they decohere. When do they ultimately decohere? When things pass out the horizon. Okay, so that's the first issue. Incidentally, my friend Ed Witten keeps reminding me that you can't build mirrors for gravitons. Maybe it's interesting that gravitons provide a way of making decoherence. But then he also reminds me that anti-de Sitter space is a mirror for gravitons. So, right. So it doesn't help you much in anti-de Sitter space. Okay. Second issue. This. You say the periodic boundary condition is a mirror. Good. Yeah, I would agree. You can't build it, but you can. Right? Okay. Right. Okay. All right. Postulate 2. Postulate 2 is this one over here. It's the frequentist postulate. The hyperfrequentist. I call Alan a hyperfrequentist. I'm also a hyperfrequentist. I believe this is what probability means. The problem is this n goes to infinity limit. Well, in eternal inflation, it's not a problem, as Alan has told us over and over again, and people repeat it over and over again. In an eternally inflating universe, everything happens, and it happens an infinite number of times. And so we're home free on this one. That's easy. That was an easy one. Eternal inflation satisfies the fact that an infinite... That's a good thing about n total going to infinity. The bad thing is it doesn't tell us how to order the events so that we can make this ratio well-defined and not equal to infinity over infinity. So you need two things to make the frequentist postulate have any bite to it, that you really do have an infinite number of trials, and that you have a way to order them, or another way of calling it is the measure, is to have a way of regulating the infinity and then allowing yourself to take. This is the wrong n, big N, n total. So this entails two things, that you have an infinity of repetitions that you have in eternal inflation, and that you know how to make sense out of ordering them or regulating them. That, so far, is absent. And this is one of the reasons I think it's so darn important to get this measure story straight. The last postulate, or the last assumption, is the really difficult one. So far, they've been easy. The difficult one to satisfy is that there really is a multiversal archivist. We express this by saying observables are observable. That was our third postulate. Observables are observable, which meant to say that the mathematical observables of the theory are also physical observables, meaning that somebody can observe them. But the problem is that there are observables in this infinite observables, the question of whether they're observable, mathematical objects, which in this infinite replication of repeated experiments, we can certainly think about observables which are composed out of two subsystems, or three subsystems, or four subsystems. As long as n is infinite, everything is repeated. But we can think of experiments which involve pairs of repetitions, or three repetitions, or four repetitions. And of course, in an eternally inflating multiverse, these things are going to be out of causal contact. And so in principle, it would sound like there is nobody who can collect data, who can be an archivist, and keep track of all of this and make operational sense out of it, or use it, to be blunt, just to use the infinite number of repetitions to collect probabilities. Okay? I think actually it's wrong to say that there is no multiversal archivist. And when I say a multiversal archivist, I mean one that's really made out of the system, somebody who lives in the system, or some system, subsystem that lives within the system. Now that raises a puzzle. How can a subsystem be big enough to record everything that ever happened in a bigger system? And the only way it can happen is if the subsystem itself is infinite. So let's discuss that. I'll come over to this blackboard and begin with ordinary de Sitter space. We talked about ordinary de Sitter space. Here it is. And let's talk about entropy bounds, because when I say a system is infinite, I, in fact, mean the number of degrees of freedom of it are infinite. The maximum entropy in it is infinite. All right, so we know that in a causal patch of de Sitter space, that the maximum entropy is finite. S max. Here's the rest of the multiverse out here. Here is the causal patch of de Sitter space. An experimentalist in here can see everything in here, presumably nothing out here, and has this much bits to make sense out of whatever he's trying to record. That many bits. And it's clearly less than infinity. Oh, let's write down what it's equal to. It's equal to pi over h squared, where h is the Hubble constant, just as a matter of fact. That's how many bits you get to play with. There's no way that you can record the entire multiverse out of that. It's not infinite. And if the multiverse is infinite, there's no way to keep track of it from within here. Okay. Now let's add the possibility that the de Sitter space is unstable. And I'm going to say in particular unstable with respect to decay to bubbles with zero cosmological constants. Things which at Stanford we call hats. And let's imagine a very late decay. Just for illustration, imagine a very late decay. Then a very late decay looks like that. Can you see it? Well, it's there. In fact, it's not all that late, as a matter of fact, on the scale of the latenesses that can occur in de Sitter space. I'll make it a little bit bigger for you, just so you can see it. If you can't see it, move closer. Okay. Now, somebody in here has a horizon, and it looks awfully much like the horizon of the de Sitter space. In fact, the later this thing occurs, the tinier this little impurity is, the more this backward light cone looks exactly like the backward light cone of de Sitter space. Nevertheless, the maximum entropy in this case is infinite. That's puzzling. How can it be infinite if the horizons are practically identical? Well, if you expand out the picture so that the people in the back row can see it, there's the picture, and the area of the two-sphere, the holographic principle, the real holographic principle. The real holographic principle says the amount of information is proportional to area. The area of the two-sphere on this backward light cones here is infinite. So that means an observer moving along here, looking back, eventually looks back to a surface, sees in the sky a surface of arbitrarily large area, and therefore has available an arbitrarily large amount of data coming in through these surfaces here. Nevertheless, it sure looked a lot like this. What you find is if you move back along this light cone here, in a fairly short and a very rapid time on this diagram, or a very rapid distance on this diagram, the area goes from being infinite at this point to being just, 4 pi h over h squared? Yeah, 4 pi over h squared. So it very quickly tends back to the de Sitter case, but the official entropy bound is infinite. And so somehow this hat has the capacity to have an infinite amount of information in it. Another way to think about it is the photons coming in. The photons come in from fluctuations down here, and they come in, and more and more and more of them come in. On the Penrose diagram, it looks like they're bunching up over here, but of course in real open FRW space-time, these photons are more and more and more redshifted, so the census taker, or whatever you want to call them, has to wait longer and longer to record them. In fact, I don't even think we need to think about the census taker. I think we can just think of the information as being recorded on the backward light cone here. It's just recorded in the form of outgoing photons. And there's an infinite amount of it, an infinite number of such photons, likewise from this side, of course. I didn't draw it on this side. And the question is, what on earth does that information describe if it's not just basically the backward light cone of this point up here? What is it describing? All right, now some of it. The first n bits, where n is proportional to S max over here, the first n photons, or groups of n photons, are, in my opinion, recording nothing but what was in the backward light cone of de Sitter space here. Just the backward light cone of de Sitter space. And they're basically being inherited from fluctuations, almost classical not classical fluctuations, but fluctuations in de Sitter space coming in here. But there's too many of them to say that all this is describing is just de Sitter space. There's too many of them. There's an infinite number of them. What on earth could it possibly be describing? What is this additional information? Raphael and I believe, and partly on the basis of black hole complementarity ideas and so forth, what it's describing is everything else behind the horizon here, everything else in the multiverse. If that's true, and if there is a good concept of horizon complementarity, we'll see how much time I have to talk about it a little bit. If there is a good notion of horizon complementarity, so that this is Hawking radiation, incidentally. This can be thought of as Hawking radiation being produced by this horizon over here. It's a kind of Hawking radiation, and to the same extent that Hawking radiation is a redundant description of the things behind the horizon of a black hole, the Hawking radiation over here must be a redundant description of the rest of the multiverse. That's our view. Can we prove that? No. But we can entertain the possibility that it's true. If it is true, then the hat itself, we can think of the hat itself and the photons that are going out here recorded on future infinity as being the multiversal archivist. That is the multiversal archivist. The idea of a census taker probably isn't necessary. All we really need to say is those photons are frozen in on the outward light cone there, and that's where the records are kept. Good. Okay, so that's our view of things, but how might we use this? How might we use this? And the hope is to use it, my hope is to use this to help us understand the measure problem. If everything out here is recorded in the photons here, then I will propose a form of measure which really does seem, in a certain sense, really operational from the point of view of observers in this hat. Okay, so let's discuss that a little bit. Let's invent the imaginary census taker who lives in here, just to draw a picture. The census taker looks back along the light cone, and as time goes on, sees more and more photons coming in. Obviously, the census taker provides a cutoff on the amount of information that can be described from this region here. Let's suppose that the information of a particular event, Alan likes to call them stories, patch of space over here, is recorded in what Raphael and I call a friendly way. A friendly way means the following. It means to decode what's going on here, which of course is a very difficult operation. Nobody's going to really try to do it. But to decode this from this, you need not see all of the photons, because there's an infinite number of them. You have to wait for eternity to see all the photons. That there is some package of photons that come out of here. Let's give them some color. Some package of the photons which come out of here. It's going to be a large number of them. It's not going to be a small number. And the coding is going to be done by studying correlations of huge numbers of photons. This is not going to be something that you look at the radiation and you see in some obvious way. That this thing over here is coded in a finite number of photons here, in such a way that for any A, we can think of the last photon that's necessary for decoding the message. Then I will say the following. If we put a cutoff, the census taker's cutoff now, the census taker's observable cutoff over here, if the last photon associated with A is to the right of that cutoff, we don't count things. We do not count A, because the census taker could not have observed it. He didn't yet collect enough photons to see A. On the other hand, if the last photon needed to record A is below the cutoff, then we count it. That would tell us whether or not to count A, and it would put some kind of surface or some sort of, I'm using the word surface loosely, for a given cutoff over here, it would tell us how to decide whether A is above or below the cutoff surface. Now, I've been studying this for the last few months. I know a little bit about how Hawking radiation reproduces information. And so I'll tell you what I believe to be the case. I believe that it is the case that if we took all experiments of a given complexity, I'll tell you what complexity, I mean by complexity the same thing that complexity theorists mean about complexity, the number of bits that it takes to describe the experiment. If you took all experiments of the type A, and you asked which ones of them are before or after the cutoff here, or let's say right at the cutoff, then it will be all experiments of type A that lie at the same height in the de Sitter space here. That means that a cutoff here will translate into a time cutoff in de Sitter space. What kind of cutoff is it? Is it a proper time cutoff? Is it a scale factor cutoff? Is it a light cone time cutoff? Well, just knowing what's going on in de Sitter space is not enough to tell you. You have to do a little more. You have to ask, in bubbles, how does this decoding work? Not this kind, just a de Sitter bubble with observers in it. How does this decoding work? That's harder. I know something about it, and I'm going to tell you my guess right now. My guess is that this provides a cutoff which is in the same family of cutoffs as scale factor cutoff, light cone time cutoff, which in a certain sense is a disappointment to me. The reason it's a disappointment is because I think it's going to lead to the end of time paradox and the Guth-Van Turin paradox. So I don't think this is going to help us escape from that. I was actually hoping that this kind of cutoff would be different somehow in some unknown way, but it looks to me like it's in the same family of cutoffs. But the basic idea is to make a dictionary or a map between events here and photons in the Hawking radiation that would allow a operationally defined cutoff procedure to be extended into the rest of the multiverse. Okay, so that's the basic set of ideas that are expressed in our paper, and I'm ready to be torn to pieces by some young person who jumps up and says, I've already ruled that out. But, yeah. So it didn't take me 2.5 hours this time.
Great job.
Yeah.
Tom?
In these pictures you've been drawing us, there's a
In which?
In the picture that's on the board,
Yeah.
there's a particular classical space-time, which is the Coma de Luce instanton for a particular decay.
Yeah.
And first of all, even if there are a finite number of points in the landscape, there are a huge number of such pictures. And second of all, I think there might...
A huge number of pictures or a huge number of types of pictures?
A huge number of types of pictures, one for each landscape. But I think there may actually be an infinity, because the types of supersymmetric vacua are continuously infinite in number, and I'm not sure that we really understand.
Okay, so
this
is...
So the question I want to ask is, are you proposing that all of those are equivalent to each other in your meta theory, or what's the story?
There may be a different answer to it. So let me tell you what another possible, that's one story. The other story that we've been playing with is that there are bubble collisions. And the bubble collisions, as far as we can tell, tend to drive this point, or the theory on this point, to a fixed point, which we think is independent of which vacuum you start with.
And also of which one it's decaying into.
Yeah, and you can have bubble collisions with other supersymmetric vacuums. That will mix them together. And you can have bubble collisions with non-supersymmetric vacuums, and that will surround, well, let's see, a bubble with a supersymmetric vacuum will do this. There's a bubble with a supersymmetric vacuum, and now we will have a gradient of a moduli across there, and the gradients of moduli will eventually, with time, spread out and form what we think is probably some final fixed point.
Okay. So
and we also think this is I wasn't prepared to talk about this, but that collisions with the de Sitter kind of bubbles will sort of surround this by a sort of common bath of bubbles, which will not depend on the starting point. So there may only be one.
In your actual theory, there's a C that depends on which place you. Yeah. So the C is somehow changing.
Well, yeah, C would change with time, but it would tend to a fixed point.
Usually, C is characteristic of a fixed point.
Right.
So is there some final right. C that's finite?
Right. So I would say that the theory starts not in a fixed point, and tends to the fixed point, so that the overwhelming bulk of the stuff coming in here from the edges will be sensitive only to the fixed point. That's a good.
Okay, I'm going to shut up because this.
Yeah.
Jim.